In this video, we're going to talk about transformations of logarithmic functions. And transformations occur from your standard a, h, and k. And I'd like to start with a because it happens first in the order of operations. So a is a multiplier, and multiplication is going to cause the graph to either stretch or compress. And what happens is you're multiplying by, in this case, an a greater than 1. So something like 3 or 5, or even a fraction greater than 1, like 5/2, would increase the values, causing a stretch vertically. Okay, and then also, if you have an a between 0 and 1, which really means a fraction smaller than 1, like a half or a third, it can make sense that those are going to compress the values. And compressions occur because the values are made smaller. So if I multiplied by 3 or 5 or even 7/2, that makes the output bigger, stretching. If I multiply by a half or a third or an eighth, that makes the outputs smaller. Now, the next part here is, why do we have an absolute value? It's actually math code for saying you need to look at the negative separately, because an absolute value would get rid of the negative. And negatives cause a graph's output to change from positive to negative or negative to positive, which causes a reflection over the x-axis. All right, and so from there, let's take a look at B. Well, B produces the key points. We talked about that in the previous video, but if you're watching this one without it, let's go ahead and write them down again. The key points for a logarithm are 1 over b, comma, -1, 1 comma 0, and b comma 1. Keep in mind that 1, 0 is the x-intercept for all logarithmic graphs. This just means write the base down with 1, and this means reciprocate the base. Now, from there, if we're talking about transformations in terms of h and k, we're talking about translations. So this is going to translate the graph right or left. This one translates the graph up or down. So in this case, h moves the graph right or left, right if it is positive and left if it is negative. Now be careful, because remember, h is always the opposite of what you see. And the reason is, anything in a parentheses in algebra or algebra 2 or even calculus is in trigonometry is actually the opposite of what you see, because you would set that quantity equal to 0 and solve it. And when you do that, right there, see how that minus became a plus? That's why it is the opposite. And you can see the same thing would happen if this were a plus, then that would become a minus. So if that's confusing, just remember things in parentheses in algebra are actually the opposite on the graph. All right, k is going to move the graph up or down. Nothing weird there. That is exactly what it is. So if you want to hit pause and write that down, I'm going to look at examples next. So those examples that I'm talking about are going to start with our key point. And one of the things we want to make sure that we do is remember that the key point, which I'll highlight them all, the key point is simply the value that comes from the bases right here. We don't want to change this. We don't want to confuse putting transformations in with our bases. We just are going to take that and we're going to apply what we learned right up here. Okay, so this would be 1/3, 1 over the base, connected with -1. We always have 1, 0, and this would be the base connected with 1. I'm going to go ahead and do all three of those. It's a good strategy if you have multiple graphing problems, and try to do the same thing for all of them. It cuts down on errors. So this one would be 1/2, comma, -1. 1 comma 0 for everything, and then 2 comma 1. This one is already a third, so when I think of -1, I need to think not of -1 makes a fraction. It kind of looks like that. It means reciprocate, so this will actually become 3. Still have 1, 0 no matter what, and this is the base that is provided, so 1/3 comma 1. All right, so looking from there, the next step I like students to do is to find their asymptotes. So the asymptotes come from h. And literally, it goes back to that solving for 0. If I set this equal to 0, I would get x equals 2. Now, initially, we call that an h. So it's h equals 2. But the corresponding asymptote is, in fact, x equals 2. And maybe that's a little easier to remember in terms of asymptotes, because horizontals, there's no y. But verticals, literally, if you set this equal to 0, you get the vertical asymptote. So here, h would be -1, for instance, and the asymptote would be x equals -1, the actual answer if you set this equal to 0. And this one would be x equals 2, while h is equal to +2. So just double check and make sure you didn't make any careless errors, and then we're going to graph those first. I always like to start with graphing the asymptotes, and the reason I like to do that is because if you start by graphing the asymptotes, it helps focus what you're going to do and what your end goal will be in the problem. Now, some students don't move the asymptote until they actually move h with the critical points, but I have found in the years that I've taught this that graphing the asymptote with the critical points and then moving the critical points after that, it kind of gives you a check. So I'm going to graph 1/3 -1, and then 1, 0, and then 3, 1. And I'm going to move these points to the asymptote by looking at the original problem, which says move to the right 2, and then move up 1 with all your values. All right, so let's take a look at what that looks like. So this will be right 2, 1, 2. This one will be, oh yeah, and then up 1. So right 2, 1, 2, up 1. That's my new intercept, x-intercept. This one will be right 2, up 1. And that blue one right there will be right 2, up 1. And this is my graph. So why don't we go ahead and just graph these? Again, it's a good idea to keep things consistent, do them all at the same time. That way your brain is in the same kind of mode. All right, so here I have 1/2. I have 1/2 common -1. So 1/2 common -1, always 1, 0. I can go ahead and put that over here if I want. It's going to be the same one, right? But let's stay focused. 1/2 -1, 1, 0, and 2, 1. And then each one of these are going to be moved to the left one. But first, I have to obey that there's a negative first. Remember, multiplication is first, and then second is any translations. Keep that in mind. So what does that mean? That negative one, that first thing you do right there, is not going to be affected onto the critical point. It's on the graph. And what it does is it makes this number right here, it multiplies this by -1. Okay, so this would become +1, negative times a negative. The intercept never changes. It's like an anchor, really. And then this one that's at 2, 1 will become -1. But we don't put it on our critical points. Your critical points must reflect the base. Don't include any of that in that particular part of the answer. Now, from here, what I will do is I will now shift the entire graph to the left 1, and that's it, because I already did that. So I just moved these red dots, left 1. It's a little big, so give me 1 second, make it more appropriate size. Left 1, and then left 1, and then left 1, and that will give us our graph. Notice that this one is going upwards and that one's going downwards. One is growth, one is decay, and we'll look at that momentarily. Okay, so here on this one, we're going to put on these key points. This has a key point of 3, 1, 2, 3, -1. Then we have 1, 0, and then we have 1/3, 1. That feels kind of weird because it feels like we did it backwards. That's just another indication, again, that we have decay. So from there, we're going to shift the graph right 2 and then down 3 for each of the dots. Okay, so right 2, 1, 2, and then down 3, 1, 2, 3. So right 2, 1, 2, and then down 3, 1, 2, 3. And then right 2, 1, 2, and then down 3, 1, 2, 3, and there is our graph. Okay, so looking at this, the easiest thing to identify is going to be the asymptote. We already did that. The next thing would be to look at the intercept, and this can be a little confusing. Like, where is this dot? It's kind of hard to tell. We know that it is 2 something, right? It's 2 something. We'll come back and look at it in a minute, and then comma 0. And the y-intercept, we can definitely tell, okay, there is nothing over here. This is none. All right, so that's why I think identifying these one thing at a time, it can be very helpful because, again, you're on that same train of thought. So this would be none. Over here, I do have a y-intercept, but it's also at the same place as the x-intercept. It is very clearly at the origin. Remember, if one of your intercepts is 0, 0, you get the other one for free. And this could have worked if you saw the y-intercept first as 0, 0, you get the x-intercept for free, but this is just the order in which it's typed on this paper. Over here, it's very clear that there's no y-intercept, so I want to do that one. And then the x-intercept, again, is 2, comma something, or it's 2 something. And we'll come back and fill that in a minute. This something is found by solving. So let's go ahead and solve these while we're doing this. And this comes actually directly from your previous lesson, lesson 2. This is lesson 3. And that was on how to solve a logarithm. Now, when you graph, you're going to specifically be solving for 0. So if I set this equal to 0, I'm looking at the first one here, and I subtract 1 on both sides, then I would get log base 3 of x minus 2 is equal to -1. Then I would base 3 this. Base 3 gets rid of this, and base 3 makes that 3 to the -1. A little hard to see, so I will write that down. You get 3 raised to the -1 power, which is a third. And then you have x minus 2. And so if you added 2 to both sides, you would get 2 1/3. All right. And that's what that question mark is there. Now, you might remember that in algebra, 2 1/3 it's an impossible thing to graph in terms of a slope. So typically what you're reminded of is that to figure this out as an improper fraction, you would multiply 2 times 3 and then add 1. 2 times 3 is 6, and add 1, and you end up getting 7/3. So 2 1/3 is an answer. The answer that is more appropriate would probably be 7/3. So just keep that in mind. When you try to solve this one, you end up getting an error. So if you want to set that equal to 0, you would have that happen. But this one over here, sorry, you don't get an error, you get 0 because so if you set this equal to 0 and you divide by a negative and then you raise it above 2, you actually get 1. I can show you that real quick. So you end up getting a 0 here. You cancel that out. You raise it above 2, and anything to the 0 power is 1, and then you subtract 1. So that's how you get 0. The error comes later when I look at the y-intercepts. So over here, if I look at this one and try to set this one equal to 0, let's actually do this one because it's a little more complicated. So that'd be log 1/3 x minus 2 minus 3 equals 0. Again, you're going to add the 3 to both sides. And then after that, okay, you're then going to have log base 1/3 x minus 2 is equal to 3, okay? And so what do you do now? Well, you have to raise it above a third. Okay, so if I raise this above 1/3, then I have to cube the 1 and the 3. And this answer is going to be wacky, right? Because it's a really weird fraction. 1 to the 3rd power is 1, but 3 to the 3rd power is 27. Okay, and then you would add 2 to that to get the other side, and you get 2 27ths, right? So x is equal to 2 27ths. 2 and a 27, forgive me. So to do that, what I would do is I would have to multiply 27 times 2 and add 1. 27 times 2 is 54, so you get 55 27ths, or 2 and 1 27. Kind of a lot for like a test, but as a class that eventually leads to upper level math, I don't think that's unreasonable in an example for notes or homework. This problem could be made a lot easier by simply changing the base, obviously, to make it a little more reasonable. However, I don't want you to just not try problems that are a little bit more difficult, especially in homework and things, just so you have that experience. To find the y-intercept, you just plug 0 in. So I just want you to remember, when you're solving a problem, like if this was a negative, you would have to plug it in and see if it worked, and it wouldn't work. This one does because it's positive. But what I'm doing here is I'm plugging 0 in. Remember, y-intercept means plug 0 in. And look what happens when I put a 0 right here. What is log of -2? It doesn't exist. Now over here, if I put 0 in here, it does exist, and you would actually want to finish it out. And the reason it's 0 is because this basically says 2 to what power equals 1, which is left over, and the only power that'll make something 1 is 0. You can also type it in Desmos if you need to see that. Over here again, if I put 0 in right here, doesn't matter what the base is, can you take any log of 0, of a negative number? And that would be no. So that's why those are algebraically equal to none. All right, this one is growth. It's going up. It's called logarithmic growth as opposed to exponential. This is logarithmic decay. and this is logarithmic decay. What is the difference between logarithmic decay and exponential decay and vice versa? The rate at which it's decaying. Exponential is very fast, logarithmic is very slow, but it happens it does eventually get to growth or decay. Let's talk about end behavior. For end behavior, we're going to look at the domain. The domain of this graph is the asymptote 2 to infinity. So we're going to write that down right here. X starts at 2, X goes to infinity. Remember, the end behavior is simply the domain compared with the range. So at 2, what is the graph doing? The graph is going to negative infinity. So we say y goes to negative infinity, or you could say f of x. And then at infinity on the x-axis, the graph is slowly going up to infinity. And you can see the growth right here. It starts small and gets big. Now over here, if I do this one, the domain of this one starts at -1 and goes to infinity. So we would have x is -1, goes to, and then this one is infinity. The domain again would be -1 to infinity, like that. And so what is the range doing? Well, right here, right, the graph is not going down here. At -1, if I go this way, the graph is going up to infinity. But over here, if I go this way, the graph is going down to negative infinity. And then let me erase that. It looks like it's pointed at infinity, but that was back when I was talking about the domain. So this would go to negative infinity right here, pointing down. And you can see this happening again. Small to big, growth, big to small, decay. So this one, the domain is 2 to infinity. So I would have x goes to 2, x goes to infinity, and then y is going up, right? So as I go this way, the graph is going up to infinity. And as I go this way, the graph is going down to negative infinity. So y goes to negative infinity. So a lot of information here. You might want to pause and rewind and look at part of that again, especially maybe as a study guide later for your assessments. And there's another part next on the graph of ln, which would simply be the same thing, but our key points will have e's in them, which will approximate as a third, or e is approximated as 2.718. But the key points have e's. All right, we'll look at that video next.